What about now? Okay, we have, sorry guys, we have a little problem with the sound here. Now it goes? Yeah. Okay, but yeah, probably the headset has a problem. So sorry for the inconvenience. Going back to the presentation, if I can. Let me see, what is it now? Sorry for this. So yes, I was saying that yeah, perhaps I should go back. So thank you to all the people that are contributing to this. We also get great support from the Dutch Organization for Scientific Research, NWO, and Leiden Observatory, who help us with the setups, with the rooms and everything. So this is not the first time we do that. This is based on a previous experience we had in Vienna in 2015 called Orion Unplugged, where we gather many of the participants that are also here today to discuss all kinds of topics related to Orion. The goal of this meeting, and similar to the previous one, is to use Orion as a benchmark of star formation studies. And the idea is to use this as a paradigm and combine or explore the state-of-the-art results and latest discoveries in this field. And we will combine theory and observations, including both instruments, so new instruments and facilities that will be open new fields in star formation. So the format of this conference is divided in two parts. The first part, that is what you are now listening and attending, is what we call the part one, the online talks, and will last for 2 days, August 26th and August 27th of 2019, and everything will be broadcasted via YouTube, and this is how you can follow us right now. The second part is the unconference part, which is basically discussions that we will have here in Leiden during 3 days, so August 28th, 29th, and 30th, and that will be for the participants that are joining us during these days here. There will be open discussions about any topic related to star formation and Orion. You can find all this information in our website, and I invite you to join us there. That includes the programs for both part one and part two, and the full list of abstracts for all our speakers, links to the YouTube streams that we are having during these 2 days, and all recorded talks after the meeting, which is part of the legacy of this conference. So you can watch and replay them anytime you want, and you want to go into details. The way you can participate in this meeting, at least or during part one, you can do it from anywhere in the world. You can do it during our online talks, basically using the YouTube live chat that you have on your window. You perhaps need a Google account to log in and be able to participate, but we already have some people posting questions there. And these would be the questions that are related to the talks that we have at that time. And we will read the questions to the speaker after the talks, and then they can reply them live. Yeah, and the 5 minutes that they should have after the talks. Another way to contribute, and this is after the talks and for any follow-up discussion, is that we have a Google group called Orion Leiden. So you can find all the instructions how to log in and how to register in this group in our website. And this is open for everybody for any question that came up either during this meeting or after the meeting or related to the meeting in connection to star formation and Orion. We have a great program ahead, as I said, for this part one. We have 2 days with different talks distributed in 2 blocks, the morning block and the afternoon block, with a long lunch break in between. The idea is that we can address audiences from all around the world. So the morning session would be more towards the Asian and Australian side, also including Europe, of course. And then the afternoon would be mainly dominated by a speaker from the US and South America, all of them live and together. The idea is that, again, you can follow them from everywhere, again, simply using YouTube and click on our videos. So feel free also to distribute this link so we get a broad audience. And so that's it from my side. We are getting ready to hear our first speaker, and I need to move back to this. So our first speaker today is Hirota-san from NAOJ in Japan. I will invite him to join. Here it is. So hello, good morning.
Hello.
Hello, are you ready?
Yes.
Yes.
So, share the screen?
Yeah, please share the screen, the entire screen. So Hirota-san will talk about high-resolution ALMA observations in Orion Source I. And let me see if I can see your, I don't see your screen yet. Okay, here, no, this is my screen. Oh yeah, here it is. So here we are, great. So yeah, you have 10 minutes, around 10 minutes. I will give you a warning 2 minutes before the end. And yeah, the floor is yours.
Okay, can you hear me?
Yeah, perfect, yeah, go ahead.
So, hello everyone, my name is Tomoya Hirota from NAOJ, Tokyo. I'm very happy to give the first talk in this conference. So, my talk will focus on the physical property of Orion Source I, which is one of the high-mass protostar candidates in Orion. So here is the structure of Orion region. As you see in the left panel, it is a very famous Orion-KL nebula. And as you see, there are many young stellar objects in this region. And at the center of this Orion-KL region, you can see very energetic outflow traced by infrared, optical, and very recently millimeter CO lines by ALMA observations. And at the center of this outflow, there is a molecular cloud and dense molecular cloud cores. And one of the core is the site of high-mass star-forming region. And the central source is radio source I, which was discovered by the VLA observations in 1995. And maybe it is hard to see, but you can see the blue contour in the left panel, which is the millimeter SIO line tracing bipolar outflow along the northwest and northeast southwest direction. And the velocity of the outflow is about 18 kilometers per second. And as you see, the structure of the large scale explosive outflow and the small scale millimeter SI outflow are completely different. So the long time ago, there was a debate to interpret these outflow structures. And at the center of the outflow, you can see the radio source I, traced by the VLA and ALMA observations. In the central, in the middle of this panel, middle panel shows the distribution of continuous emission and SIO measures traced by VLBI and ALMA. Detail will be presented by the next speaker, Megan Kim. And you see the rotating structure perpendicular to the outflow. And recent high-resolution observations show very clear Keplerian rotation curve, which will be discussed by the talk of by Adam Ginsberg later. According to the position velocity diagram, the mass of the central source is estimated like 5 to 8 solar masses or 15 to 20 solar masses. And detailed analysis and interpretation will be presented by the next talks. And this source is the central position located at the center of the explosive outflow and bipolar outflow. And the it is hard to interpret this result. According to the recent observational studies, source Y was affected by the close encounter event, and as a result, the explosive outflow are ejected. But we have question: is Orion source I typical protostar, a high mass protostar, or a very special source affected by close encounter event? So we are interested in the detailed property of this one of the nearest high mass protostar candidates. So we are conducting high resolution observation with VLBI and ALMA. Today I will talk about our recent results from ALMA observations at high resolution, 0.1 arcsecond resolution, which corresponds to 40 AU at the distance of Orion. And this is the summary of our observational studies. We have conducted many ALMA observations ranging from band 3 at 86 GHz to up to band 10 at 800 GHz. Today, I will mainly focus on the band 7 and 8. And we have detected many molecular lines, but today I will focus on the SIO and water lines because they are turned out to be the very good tracer of the outflow and disk, unlike organic molecular lines, which could trace larger scale molecular cloud core, hot molecular cloud core. Probably we will see some discussion about molecular line observation in this workshop, but I will only focus on the water and SIO line. And these are the results from our first observations. As you see, there is very compact structure traced by high excitation water lines and SIO lines. And you can see velocity gradient perpendicular to the outflow. And we also see the velocity gradient in the high resolution water line and SI18 line as shown in the bottom panels. Even in the outflow lobe, we see rotating velocity gradient, which implies rotation. To see velocity structure more in detail, we made position velocity diagram along the many cut lines as shown on the top right panels. You see two kinds of different structures as shown in the bottom panels. Close to the disk midplane, you see Keplerian-like rotation curve with the velocity gradient, which implies 8.7 solar masses. On the other hand, you see inclined elliptical structure at the further distances from the disk midplane. It can be interpreted as a rotating expanding motion. And we can measure the expanding motion of 10 km per second. So I will skip in detail about the model, but our results are consistent with the rotating outflow as shown here. So left panel is the observational result and the central middle panel is a schematic view of our result. And the right panel is a possible interpretation of the theoretical model. So we see the rotating outflow, which can be explained by the magnetic centrifugal disk wind model. And launching radius of the outflow is about 20 to 40 AU, which can rule out the possibility of X-wind model. And we could not see high velocity jet with a velocity of more than 10 km or 100 km. So the outflow can be directly driven by the disk wind rather than the entrainment of the collimated high velocity jet. And thanks to our high resolution observations, we could estimate the basic property of the outflow, such as momentum rate, momentum, kinetic energy, mass loss rate, momentum rate, mechanical luminosity, and so on. And we could compare our result with those of a massive outflow survey conducted by single-dish observations. And basically, the properties are almost common, except for the total mass, total momentum, and total energy. But the mass flow rate, outflow force, and outflow power are almost consistent with those of the 10 to the 4th solar mass sources. But we have to notice that density is assumed by the critical density of the SIO line.
So Hirota-san, you have 1 minute.
1 minute, okay. In order to constrain the density, we need more detailed mass-transition studies. I will skip the detail, but we already have many molecular line data from the water and SIO as shown here. They can trace disk, and they can trace outflow. And detailed properties are summarized here. The lower excitation lines could trace outflow, and higher excitation line could trace disk. And combined with the theoretical model calculations, we will be able to constrain the more detailed property of the outflow. So we could see the very ordered, very normal bipolar outflow in Orion Source I. So there seems no peculiarity caused by the dynamical encounters. This could be explained by the strong magnetic field. This figure shows the magnetic polarization structure traced by the SIO and the SIO lines by using VLA and ALMA. So you see very ordered polarization structure, which could suggest ordered magnetic field. So detailed analysis will be done soon. So time is running, so this is a summary of my talk. Thank you for your attention.
Yeah, thank you very much. Oh, really good, really good. Thank you for the excellent talk. So you can keep your presentation if you want, because now we'll see you and the presentation at the same time. Mm-hmm. So we have a question from Jan Fabrich. So who asks, what do you think? So to what degree could observable properties of source I as a high mass protostar be unique due to its dynamical history in the ONC? So is this a unique source, or is it a more general case of high mass star?
Yes, according to the disk and outflow properties, we couldn't see any peculiarity, at least from our observational result. So it seems very one of the bigger high mass protostellar objects. Of course, we need more detailed analysis and detailed discussion.
Mm-hmm. No, really good. I also noticed, I have a question myself. So because you talk in terms of the critical density of SIO, which is really, really high. So are you suggesting that the whole thing is at this critical density, or so which parts of the disk or the wind would be at these densities? Because it looks like 10 to the 7 or so.
Yes, I assume the critical density of the SIO 11 to 10, as shown here. Yeah. Can you see the map?
Yeah, you put it in full screen is better for the audience to see it.
Yes, in the left panel, I show the SI 18O J equal 11 to 10, which has very high critical density. I assume this structure. Yeah. So this is a very dense central part of the outflow.
Mm-hmm. It should be this different compared to other outflows?
Yes.
Low, high mass outflows?
Yes. According to this survey, the results are from single dish observation of CO line, which could trace lower density but larger scale structure. Mm-hmm. So that's why I could compare mass flow rate, outflow force, and outflow power, rather than mass, momentum, and energy.
Great. Thank you. Yeah, so it was a great talk. Yeah, we do not see more questions from the audience, so we will thank the speaker again.
Thank you. I will stop the share.
Yeah.
Stop screen. Okay.
Thank you. Sorry. So our second speaker today is Mi-Kyun Kim. Sorry if I mispronounce your name. So can you please share your entire screen?
Okay.
So Mi-Kyun Kim from NAOJ, also from Japan. She will talk about the extremely high excitation SIO lines in Orion Source I.
Is it okay now? You can see my presentation?
Not there yet. You need to share the entire screen.
Oh, okay.
In the meantime, I would like to remind the audience that that you should make your questions in advance, because there is a little delay between our broadcast and the YouTube channel. So please do it before the end of the talk.
Okay.
But yeah, so yeah, we can now see your presentation. So the ground is yours.
Okay. Hello, my name is Mi-Kyun Kim, and I'm working in NAOJ now, but I'm in northern side of Japan, Mizusawa. So I will talk about the detection of extremely high excitation SIO lines in Orion Source I. Actually, already Hirota-san gave a nice introduction to the Orion-KL and Source I, so I will just give a short introduction on this. And this is the Source I is the nearest high-mass protostar candidate from with a distance of around 400 to 420 parsec. So as already Hirota-san introduces, there is many unsettled problem on this source, like the mass of source I and whether it is a single star or a binary system, and they are just formed by a accretion on a single core, or there is some dynamic interaction between multiple stars like that. But actually, for this source, we just can see very clear outflow and disk system like this. Here you can see some SIO thermal line from KARMA and SIO line from ALMA observation in the middle panel, and it shows very clear rotating outflow system and perpendicular disk. And very inside of the outflow, we can see very bright SIO measures, which is unusual in star-forming regions. So we have many high-resolution observations for this source, but still we don't know about this source in detail. So many more and more higher resolution observation is conducted. So this source will give us the most detailed picture of the dynamical structures around the protostars. So today I will present the result of some ALMA observations towards Orion Source I with high excitation XIO lines. The observation has been conducted in 2015 as one of the ALMA Cycle 2 science program at Band 8. The PI was Hirota-san. And we had a spatial resolution of around 30 to 50 AU at Orion distances. And I will show you the result of these SIO line results with excitation temperature of 3,000 to 90,000 Kelvin. So toward the source I, we detected all three SIO lines, especially this is the first time to detect SIO V4 line in star-forming regions. This line has very high excitation temperature of 7,000 Kelvin, and it has been detected in only evolved star, like VY Canis Majoris. So this is the first time detected in star-forming regions. As you can see in figure, all three lines shows very clear double peak profiles with the velocity range of around minus 30 to 30 kilometers per sec. This is very similar to other thermal SIO or edged line and SIO majors. So even in these high excitation emissions, we couldn't detect any high velocity components, and it means the outflow is very steady in all scales. And in the left panel, SiO-V2 spectrum, you can see there is some absorption profile around minus 20 kilometers per sec. But this is also have a very high excitation temperature of 3,000 Kelvin, so we don't think this is a self-absorption, and the possible candidate is SiO-V0 line with a velocity of minus 1 kilometer per sec. So this velocity is consistent with the blue shifted components of this outflow system rather than other structures like hot core and compact reach in here. So we think the absorption is originated by the materials in the disk and outflow around the source I itself. So next, we will show the spatial distribution of the emissions. In this figure, the white contour represents the continuum emission in same frequency range, and the gray contour shows moment 0, and colored map shows moment 1 maps, first moment. So in 29, SiO-V2 and SiO-V4 shows very quite compact and circular distribution, but SiO-V2 line shows very clear bipolar structures perpendicular to the elongated continuum emissions. And also, you can see the velocity gradients in all three lines along the northwest to southeast directions. It's consistent with other major observations. And also, in 29 SIO and SiO-V4, you can see there is a small offset from the continuum peak. I mean, the peak position of the SIO emissions are a little bit offset from the continuum peak. It is already reported by previous thermal line observations like Plumbaker, right, 2016, or Ginsburg et al. And it suggests that these lines are not traced to the disk midplane. They are just located on the surface of the disk. So we, to clarify the structures of each emissions, we tried two-dimensional Gaussian fitting to each velocity channel of the emissions. So in these three figures, gray dots represent the position of the 43 gigahertz SIO majors observed with the Vera, and colored mark represent the SIO emissions observed with ALMA in this time. So first, in SiO-V4 and 29 SiO-V2, you can see the colored mark, I mean the high excitation SIO emissions is displaced from the disk midplane as seen in previous moment maps. But SiO-V4 line is very linear and compact structure, but 20 SIO line has some vertical structure from the disk midplane, like this blue shift components. And in left bottom panel, you can see both SiO-V2 and 29 SiO-V2 line position, but actually SiO-V2 line is a little bit extended structure in the channel map, and I picked up just a few bright compact peaks, so it is just give you some rough estimation of the their structure. Is not so precise, but still you can see the emissions are distributed in the in outflow lobes, and the opening angles of these high excitation SiO lines are consistent with the position of the major line, 43 gigahertz major line. So you can see these high excitation SiO lines trace the very inner part of the outflow, and the 43 gigahertz SiO majors are tracing the surface of the outflow, maybe shocked region of the surface of outflow.
So you have 1 more minute.
Okay, so as you can see, the SiO-V4 line has very linear structure and show clear velocity gradients. So we try to fit the rotation curve of the V4 line with a simple ring structure, rotating ring structure. It gives the central mass of the 7 solar mass and the inner radius of 12 AU and outer radius 26 AU. Actually, this 7 solar mass is just a lower limit of central mass, because as you can see in the left panel, our observation has not enough spatial resolution and sensitivity to clarify the structure of the V4 line. But our results show that this line traces a very inner side of the outflow, where outflow is launching from the disk, and its distance is smaller than 30 AU from the star. So maybe it is a good tracer to study the kinematics of the outflow launching region with higher resolution observations. So this is our summary. Yes, yeah. Thank you.
Thank you very much. Yeah, really good. So while we wait for some questions here from the audience in Leiden, I have a question myself, because you can leave if you want the presentation in full screen so we can see.
Okay.
It's up to you. Yeah. So you mentioned that this is the first detection in a star-forming region. Yeah. So I'm just as completely ignorant of these things. So why we didn't detect this before? Is because we didn't look for these things, or because the conditions in this source are so extreme that we only detect these highly excited lines in this particular Orion I source?
Maybe both. Maybe I'm not sure that there are many.
Somehow,
there are.
No, sorry. No. Okay. No. Sorry.
Can you hear me?
Yeah.
Maybe the survey of this high excitation SiO line toward the star forming region is very maybe no survey or very few, and actually the SiO major also very unusual in the star forming region. So I think this source is a little bit unusual in that. In that way. So I don't, I'm not sure why, but actually, yeah, it's quite an unusual case, I think. Yeah.
I have a follow-up question in this sense. So a question also from Jan Polbrich. So what are the prospects and options of observing the jet launching region at even higher resolution? So are you trying to do this in much higher detail? Can ALMA do it?
Yeah, maybe It's a cycle 2 data, so already maybe we can get more higher resolution data about this source. I don't have data yet, but anyway, in our data, as you can see, we don't have enough resolution to resolve the clear structure of this one. So, and this is a very inside of the outflow disk system. So, if we can see the more detailed structure in here, then we can see more. We can get more information of the physical parameter like the central mass and some velocity field in the outflow launching region like that.
And I'm sure that will make a great follow-up proposal for the future. So that's really good. Yeah, so thank you very much. Thank you again. Bye. Good. So our next speaker today is Laurent Parani. Let me put this low. Yeah, Laurent, do you have a headset because there's some echo in the broadcast?
So, say it again.
Okay. Will you have a headset that you can use? Or at least perhaps as soon as I mute my phone should be fine. But now there are some echoes. Yeah, that would be best. Yeah, so Laurent Parani, he works at the observatory in Paris at the CNRS, and he will talk about the complexity of Orion and ALMA view. So Laurent, if you can, yeah, I see your screen here. Yeah, so if you put it in full screen mode, then we'll all have it here. So your own presentation in full screen.
Yeah, but it didn't propose me to put full screen.
Yeah, you need to put the screen share in entire screen mode, and then you click on your own presentation, and then you make it also full screen. Because we saw your presentation, but was small in the window.
Yeah, I know it's small, but I have two screens.
Okay. So now we lost your screen share. Okay, now it is back. So it's loading now.
Yeah, but it takes.
Can you put it full screen now?
Can I try to? Oh shit! Sorry. Well, when I tried on my own, it was full screen like that, but not now.
Yeah.
Is it better? I've
no, it's still small in the screen.
And it's
make the window larger. Okay, now let's see.
Well, it left.
Still small.
And it collapsed. PowerPoint crashed.
Okay. do you have a PDF version which will?
No. No.
Okay. You can generate one.
Yes, I guess I can do that. Maybe you should move to the next speaker, and I come back later on.
So so Jaime, are you ready? Yeah. So we will move them for the next speaker, and then we'll back to you. So please generate a PDF, and then we'll be back. Okay.
Okay, I try to do that.
Good. So no problem. We are here ready for this thing. So we have Jaime from Hertfordshire. So sorry for the sound. I'm trying to make it. Yeah. So Jaime, so he's from the UK, or he works in the UK, and he will talk about the Orion Radio All-Stars VLA observation of clustering, proper motions, and variability in the ONC. So Jaime, if you can share your screen. Yeah, I see it here.
Yep, I think so.
Good.
Perfect.
And now also
and can you hear me nicely?
The ground is yours. Yeah.
Thanks. Hi, everyone. Well, I will show you what I've been doing this year at Hertfordshire. This is a project that consists in a follow-up of the compact radio population towards the ONC. In the center of this region, there are 100 of young stellar objects that can emit at radio frequencies. And this emission is due to two main mechanisms, non-thermal and thermal emission. But let's look first at the classical diagram from Figelsson and Montmer that shows the main stages of low mass young star evolution, going through class 0 infalling protostars, going to through Tetauri stars, until reach the main sequence. And in all of these stages, we can see a X-ray emission and also radio emission. The non-thermal radio emission is produced. It can be seen at centimeter wavelengths and is produced by Yari synchrotron emission from merely relativistic electrons urinating along magnetic field lines. And the thermal radio emission is produced by free emission from ionized material that can be caused by stellar jets or outflows. And on the other hand, the X-ray thermal emission is produced by heated plasma from the energy released from magnetic recognition. And this is shown in the right panel, and where we see the Tauri diagram, and where we see the accretion disk and the magnetosphere of the Tauri. Then the extension of the magnetosphere interact with the accretion disk, and that produces the magnetic reconnection. And in this magnetic reconnection, the energy release is the one that heat up the plasma produced in the thermal X-ray, and then this also energetic energy release also accelerate the electrons that are urinating along the magnetic field lines that produce in the thermal emission. So, and this is the scheme that from Waterfall 2019 that shows that this magnetic reconnection produce flares, and these flares produce variability, and variability has been seen towards young star objects, and particularly also all these works. But toward the ONC, there have been observations in the radio domain prior to the VLA upgrade until Zapata with the deep catalog, and then after that, VLBA observations for momentum, for example, where we know some accurate measurement of the distance. And particularly, I want to mention the deep catalog produced by Forvik 2016. That is the catalog I've been using as a reference, because if you want to see more about this physics, see the talks, Colombo and Reed. So the catalog that produced Forvik in 2016 is VLA data 30 hours in the central pointing. But what I got now is 30 hours also, but with 6 additional pointings. So the central pointing is the same setup of the deep catalog, and the setup for this additional pointings is also the same, but just 4 hours each, using the C-band and the high resolution A configuration. Here in blue dots, I'm showing the X-ray catalog cube from Jetman 2005. And the coverage with the new observation setup can cover the cube area also. And the red dots correspond to the deep catalog that, of course, is covered the area of the central pointing. So what I released the data using CASA, and the fittings and extraction of the parameters for the source was done with infit also in CASA. So I'm showing here the distribution of the source. In green is the new detections, the detection from all these pointings. In blue also the X-ray catalog from cube, and red again the deep catalog. As a reference, here is shown the trapezium, the Orion-KL region, and where this Orion source I that was accused in the previous talks. The distribution here is not homogeneous, as we can see from the distribution of the green points. And in order to quantify this non-homogeneous distribution, what I did here is divide the pointings. And in green, I'm showing the detections from the new observations, which is not quite homogeneous. But interestingly, I also make the counterpart with X-ray emission and infrared emission from vision and cube, just to make an estimation of how high is the fraction of this detection in the new observation are correlated with probably a stellar counterpart, and not entire detections probably are not related to stellar. So our compact detections from VLA data might also not necessarily correspond to stellar emission. And also in black here, I'm showing if there is some fraction of the sources per pointing that has some previously known radio observations, and there is a high fraction of sources that were observed in different radio observations with VLA. But particularly, I want to show you the central pointing that our new observations are not that sensitive that as the deep catalog was, and still we are not getting the entire detection in the deep catalog. So there are new sources even with this less sensitive image observations. So a direct comparison that we can make is a comparison between the two catalogs, taking the fluxes, the average of the concatenated images, just to target some extreme variabilities. So what I first did, take the sources that has counterpart in the deep catalog and make a peak flux ratio just to make comparison how different are the fluxes, and also the opposites, using the new catalog over the previous one and the deep catalog over the new observations. And particularly, there are listed in red the flux ratio for the new observations. There are particularly at least two sources in the new observations that has peak flux ratio over 10, even over 12 around. So these sources are these ones. Here I'm showing the peak flux and signal to noise ratio in the new observations, and the peak flux and signal to noise ratio in the deep catalog. So they're quite high, especially for the second source. And also it was possible to determine some spectral index from the deep catalog. These two sources has X-ray counterpart, infrared counterpart. One of them was also observed in previous, in Zapata et al., in Kunkel, and also in Sheehan. So this has like primary targets to analyze in extreme variability areas. So what also did is now take the detections that were not detected in the deep catalog. That is a bit surprising since we're using less sensitive image. But this is also a hint that we're looking at extreme variability. And what I did here is take like a variability factor that is mainly the peak of the current observations over the 3 sigma of the deep image. So it kind of shows how would be the detection of these new sources in the deep catalog, and they actually shows factors of over 5, 6, close to 10. So that is quite high, even with this lens sensitive image. And these 4 sources here also have X-ray counterpart, infrared counterpart that could be then a counterpart of a stellar source. And the signal to noise ratio can be that high as 80, for example, or 50. So this is are good targets to also analyze for spectral index, for example. And none of them were detected in previous radio observations, not in Zapata, in Kunkel, and Sheehan. So now a similar comparison can be done using the non-detection sources in the new catalog that were detected in the deep. That makes sense since it's more sensitive. And in this case, with this variability factor, taking the peak flux in the deep catalog over the 3 sigma of the new observations, doesn't mean that we're necessarily looking at extreme variability that now they are faint. It only means that those sources just are too faint to be detected in the new setup. So that's the conclusion from this low variability factor. So from this comparison, I'm taking the flux averages over the images. So these are only lower limits for extreme variability. So what happened, and it was shown in 4 collaborators through 2017, is that these are light curves of a source in the deep catalog, and where they have 5 epochs. And in blue dash here we see the average flux of these sources in the concatenated image. But we can see that in a single epoch, the peak flux can be 3 or 4 times higher than the average flux, and this is hidden in the concatenated flux. And even if we go to time range, here take time scales of 30 minutes. And in this 30 minutes time range, the peak can be even higher. And they went to even shorter time scales of 6 minutes, and it can be even more extreme. So what we are not we're looking in these previous ratios are just lower limits for extreme variability, and in these fluxes can be hidden this effect. So the next task would be produce the light course to get and trying to find some extreme variability in really short time scale. So additionally, what we can do with this VLA observations, since we're using the extended configuration that with interferometry we can get accurate positions, we can directly compare the two epochs, the deep catalog and the new one, and get some proper motions. But in this short time scale between these observations, 2012 and 2016, only 4 years, one wouldn't expect some high proper motion, what we actually found. And what we have here is the diagram of proper motions coded by transfer velocity. And the full sample is, there's still a high dispersion probably, but it's still around 0. But even with this dispersion here, there are some extreme sources with transfer velocity above 200. So what I did just to take the more extreme cases, and they made a cutoff in transfer velocity, take everything above 250 kilometers per second, to see where they are located in the image. They are not randomly located on the central pointing. As a reference here, I put the trapezium, the Orion-KL. They are in the north side. That would may make them interesting because they are located in the side when there's supposed to be a explosive event a time ago, and it was studied before. So taking just an example of these extreme cases, what we see here, this is the deep image, and in green we're looking at the new positions from the new observations. And it is not only a compact source, it's also an extended emission that is moving with the compact emission. And it is also correlated with the near infrared from 1.6, I guess, micros from John Bailey data. So for more about proper motions, see the talk from Sergio Cid and McBride tomorrow. So what's next is to take this previous extreme variability that I show and make the short time scale slide curves, and also make the analogy comparison with the Chandra simultaneous observation that we got for the same central pointing. Here I show the central pointing, that also the Chandra observations extend to the outer pointings. So that's it. Tomorrow there will be also a talk about extreme variability from the James Clerk Maxwell. Well, yeah, thanks.
Good, really good. Yeah, thank you for the talk, Jaime. So we have one question from Leiden, from our audience. So Sierk van der Wiska, he asks, can you identify the cause of extreme variability in short time scales?
Sorry?
Can you identify the cause of this extreme variability? So how or what produces this extreme variability in short time scales? What is the physical mechanism?
Oh, I can show, for example, this is came from waterfall.
Can you make it full screen? Then yeah.
Yep.
Great.
So the interaction between the electricity and the magnetosphere can produce some magnetic reconnection activity, and these events can release a significant amount of energy release. This energy release can heat up the plasma, producing X-ray emission, and also this energy release can accelerate the electron generated in these magnetic lines, producing some strong emission in radio centimeter wavelengths from non-thermal emission. In between, probably it's more because of that. This is one.
Good. Thank you. We have a direct question from the audience here, so I will pass the word to Joao Alves.
Can you repeat your reasoning on the cause for the high velocity stars?
Yep.
I missed that.
What for the what?
So they're clustered on the north, and what?
It is here. So this corresponds to the central pointing image in the background. Here there's a red circle centered in the center. This has a radius of 2.5 per million. Yeah, here is the trapezium, Orion-KL,
Right.
and I cutoff velocity of the higher motions.
Which you said is 15 kilometers per second.
15? No, the cutoff that they made is 250 kilometers per second, which is quite high.
So these sources have velocities of
Above
250 kilometers per second.
Yeah, I'm using. Yeah, that was the. We wouldn't expect to find this kind of motions.
That's amazing.
That's crazy.
And why do you think they are? What's any
idea?
idea?
Most of them are related to the event that came related to the explosive.
They're not stars. Okay, good. So sorry.
No, really good. Yeah, it's great that it creates a lot of discussion. That's nice. So we have another question from the audience. So Marina Konkel, so she asks, have you gotten the chance to compare your radio variability rates to optical and near infrared, like a variability as well?
With optical, pretty sure. Yeah, I'm not pretty sure how can I relate it with the optical counterpart.
Okay.
Indeed.
That would be a nice follow-up, I guess.
And
we
can take, it would be great to have the Vista, the improved vision. We can do variability analysis. Recently, I didn't share.
Now, I have a question myself, because you were showing the distribution, the spatial distribution of your different pointings and different detections. Do you have any, or do you see any difference depending on the field in terms of variability? You have more variability at the center or not? It's more or less uniform, or you didn't have the chance to?
Between the outer pointings? Yeah. Unfortunately, I cannot make that analysis because the comparison I'm making is with these new observations with the previous catalog. In the big catalog was obtained with only having 30 hours in the central pointing. So yeah, the comparison was directed to that catalog. I don't have like another epoch.
No, thank you very much. So thank you, Jaime. So, good. So we move on now. We go back to Logan. So can you now share the screen? I think it was working in the test that you were running in the background.
Yes. Okay, I have to click here. Okay.
Yeah.
Are you?
Now it works. Yeah, now it works. Yes, it works nicely.
Okay.
Yeah. So Logan, as I said, he's working in the Observatory of Paris and for the CNRS. Yeah, he will talk about the complexity of Orion and ALMA view. So the ground is yours, Logan.
Thank you. So it will be a fast talk, of course. I'm going to show you a number of results we recently published from cycle 2 observations of Orion-KL region, especially this very nice continuum map showing all the infrared cores and interesting parts we've been studying. And if we compare this 1.2 millimeter dust emission map to a 12 micron map, we see there are big differences between the two. The NKL is much stronger at 12 micron, but also the hot core seen at 1.2 millimeter is not seen at all in the 12 micron. So I move 12 micron away, and you see that the two peaks are outside the hot core part, which means that this hot core, which should have been seen because it's very hot, is masked by cold dust in front, which is optically thick at 12 micron. That's one result. It was also mentioned that there is this explosion in the center of the region, and the explosion is seen through various objects. First, the I and BN stars are moving away. not N anymore, which has been found to be static, in fact. And also we see H2 fingers and 12 CO fingers showing very nicely this explosion going on. It was about 550 years ago, and this is not my work, so I send you to these papers to know more about them. But it has a lot of impact on the KL region, as I'm going to show you now. But first, well, very quickly, we found some species in Orion which were not reported in that source before, but which were already known, like the propyl cyanide NNI isomers, which were discovered in Sagittarius B2 before. We found them in several places, and we found a varying ratio from 2 to 6 across the region. And this 2 to 3 is about the same as the 2.5 found by Beloche in Sagittarius B2, but here it's lower. And this ratio depends on the time it takes for the warming up, if you see Garrett's paper in 2017. So his fast time scales are still 50 to 200,000 years, while here, if we are linked to the explosion, it's only 500 years. But this might be accelerated thanks to a strong UV field, but still an open question. Other species we found for the first time in this source, but which were known elsewhere, is acetic acid and the J isomer of ethylene glycol. The A isomer was already found by Brouillet et al. In the SV0 data. And the three species are all seen at a very small spot here, for the three of them, which is away from the hot core itself in a non-conspicuous place. And we propose that this was due to a bullet starting from the explosion center, which is about here, and which hit the dense cloud here, provoking some evaporation. Note also that the acetic acid to ethylene glycol ratio is about 2 in our source, while it was only 5% in IRS 16293 in the Jorgensen paper. So it's a big difference we have to explain. By the time we wrote our letter, there was one by Wright and Plombeck about very high resolution observation of HC3N. They found a shell of this species and other species exactly at the same place as where we find acetic acid and ethylene glycol, which confirms the idea of a bullet making a cavity at this place and evaporating material locally. Now, next, when you want to study this region, looking only at integrated lines intensity is not the best way to study the source, we think. You should look at the line shapes where you can learn a lot of things. I don't have time to go into many details, but here we have ethanol and ethyl cyanide and vinyl cyanide, and the three are very different for each place. So compact ridge, core, different infrared clouds on metal format peaks. And you can see that several places, hot core, RC721, MF2, have velocities which are below 7 km per second, and usually a blue wing. If you look at MF4 and MF5, which are on the right-hand side of the explosion center, they are at higher velocities than 7, about 9 to 11, and they have always red wings. This is very conspicuous here. And that's one information about velocities. Another information we found is looking at the methyl cyanide towards MF5, for which we know there are 3 velocity components from other species. And these 3 components are optically thick in this 12.3 to 11.3 transition. And the way we combine the 3 of them on the line of sight makes different profiles here. And the only one profile we obtained is coincidental with the observations, which gives you information on the position of the 3 components on the line of sight. Finally, the compact ridge region is very different from everything else. It has symmetric wings, unlike the others.
and very narrow lines, again, unlike the others, which are about 3 kilometers per second, typically, up to 7. And so we think this compact ridge is not completely related to the rest of the region. It's so we end up with a kind of 3D sketch of the region. From the front view, you have the hot core here with MF2. You have RC7 and MF12 compact ridge below, and MF4 and MF5 on the right-hand side. And since these are at low velocities compared to the mean one of 7 kilometers per second, and these are high velocities, we think that they are in front of the compact ridge of the explosion center and are pushed towards us by this explosion, while MF4 and MF5 are rather moving away from us. And also the blue wings here are due to the explosion wind grazing these dense regions, picking up the gas, taking it away with it. So we get only blue wings here because it's coming towards us, and we get red wings because it's going away from us here. And the compact ridge is far behind because we found in the I-star outflow, SIO outflow, some interaction with the compact ridge at 13 to 20 kilometers per second, which means the redward expansion of the SIO outflow, which means that the compact ridge is behind. The second part of the talk is about channel-wise maps of a few species, like OCS. And when you look at individual channels, you find that the gas peak emission is not coincidental with the dust peaks and is extending away. And usually, especially in some cases, the expansion is pointing back to the explosion center, here, and here. It's very conspicuous. And you see that the peak emission is displaced on these lines. This is true for some species, but not for others, like ethyl cyanide. The expansion only at 0 to 2 kilometers per second is visible, but for the other velocities, it's much weaker than for OCS, which probably means that this species, after evaporation from the ices, is destroyed relatively quickly and disappears from the region. So we have a problem here between methanol and ethyl cyanide, which are supposed to be both evaporating from ices, but towards IRC4 MF12 peak here, we have a big problem because methanol is only emitting at 7 to 10 kilometers per second, while ethyl cyanide, vinyl cyanide, and cyanoacetylene are all emitting mostly at 0 kilometers per second, which has absolutely no emission for methanol. And we have also some problems with other species like methyl cyanide, which is stronger at the velocity of methanol than at the 0 kilometers per second. Also DCN, which is stronger at 7 than at 0. So it's very confusing. And we are wondering if some of these species are not formed in the gas phase as well as on ices. And finally, we observed a number of deuterated species. Only the deuterated species which were formed on the ices can be seen. So N2D plus and DCO plus are not seen in this source at all, because they are only formed in gas phase and it's too hot for them to be formed. And the interesting thing is D2CO has the similar expansions as H2CO, its parent isotopologue, while especially NH2D only evaporates from the grains and is destroyed immediately, converted back to NH3. And because there are no similar extensions as what we see here for the other species. This has been checked with a chemical model. We started with high deuterated abundances of the different species, and we let them evolve with time. And we find that in 500 years, so just the time of the explosion, the NH2D has decreased by several orders of magnitude, 1 to 3 orders of magnitude, depending on the conditions of your model, while D2CO hardly diminishes by a factor of 2 to 3. and H2CO and H3 do not vary very much. So this
You have 1 minute, Laurent.
And this means that the explosion is helping us to follow the chemistry evolution of the cloud as a kind of time-flying experiment. So in conclusion, we found that people before us found also that oxygen carriers and CN carriers of comps are very different. But here we have very precise examples of differences which should be investigated. All the region is under the influence of the explosion which happened 550 years ago, except the compact ridge, which has probably not been reached yet. So this put a distance for the compact ridge about 10,000 AUs at least. And so we can explain all the asymmetrical line wings and these kind of things. The bullet coming from the explosion to explain acetic acid and ethylene glycol. So we would need to explain why in other warm regions these species have not appeared. It's not clear for us yet. And the spatial position of species which are linked to their chemistry, to the evolution of the chemistry, which should be investigated in more detail in the future. And as we explained, especially for the decorated species. And I thank you for your attention.
Well, thank you very much. Yes, let me switch now to you a bit. Yeah, so we have a question from Jan Folbrich. So you can leave the window to the presentation on if you want.
Yeah.
Or we can switch now here. So the question says, so based on these results, is it possible to make predictions for other observable molecular lines that will offer complementary information in a way that was not clear before? So can you think on new observations that can clarify your different results?
Whoa. Well, we still have to try to understand all the data we have before trying to make more observations, I'm afraid. There are so many informations buried in the data yet, and we have not understood everything. Probably we should first analyze this in more detail. What we have done now is including the zero spacing, which we were missing before, so we can make quantitative analysis, which were not in the original papers.
Yeah, that sounds exciting to see the results with the combined data.
Yeah.
So I have a question related to this, is because you are talking about the chemistry and molecule scene excited by this explosion around, but it's also a really complex region with really high density, so it will produce its own chemistry. So can you disentangle the two? Is easy, or you have this is what you are exploring now?
Well, yeah.
Sorry for the question.
Yeah, it's very. Yeah, I'm a newcomer to Orion. You probably know I was not there in this region before, so I still have a lot to learn. I'm sorry, and I hope to make to understand better. Yes, the explosion itself, except one of the things is really to understand this ethylene glycol and acetic acid problem, because why is it only where the bullet hit the cloud, not everywhere else, where we have temperatures of 300 K, like in the hot core, so everything should be evaporated, including acetic acid. So why don't we see it everywhere else? That's a big problem. And if we understand that, maybe we make some big progress on what goes on in the dense parts and what goes on with the explosion.
Mm-hmm. Yeah, just to follow up, we are all kind of new in Orion, so this is why we have this conference here to share all the results. So I hope you can also contribute in the forthcoming meeting that we'll have in the future. So we have another question from the audience here. So let me pass the question here to Jérôme Petit.
Bonjour, Laurent. About the deuteration in the freeze phase, is it coming from the H3+ or the CH3+ path? Is it the standard way, or is it the warm deuteration chemistry?
It must be the standard chemistry before the stars switched on.
I think, because I know CH2D plus would work in the 50, 70 Kelvin range, but here it's much warmer than that. So it's probably not working anymore either. So it's all based on the ices, and the ices were formed in the cold past when it was below 20 K. So it must be H2D plus chemistry.
Really good. Yeah. So thank you, Logan. It was a great talk. So thank you again. Good. So we move on to our last speaker of the session. So we have here, Sergio Zip from the Max Planck Institute for Radio Astronomy in Bonn. So Sergio will talk about high angular resolution radioastrometry to YSOs in the ONC. So Sergio, you can share your screen.
Hi, can you hear me?
Yeah, we can hear you.
Okay.
Yeah, everything works. So if you can share your screen, I can put it on the stream. So again, as another reminder, so for the audience, please make your questions a few seconds before the end, because there's some delay between what you are hearing and watching on YouTube and what we are broadcasting here. So you can share a full screen, your entire screen.
So I have a problem. I just see that during the test I used one browser, and now I'm using another one.
Can you just simply share your screen on
the other browser?
If you have your...
I will change.
Okay.
Sorry.
Oh. So we lost our speaker suddenly. So I need to entertain you for the next few seconds. He's back. So now you're here. Yeah. I can talk about Orion if it's necessary, so that's not a problem. So yeah, you can now share your screen. Yeah, now I see you. Yeah, you can put your, yeah, perfect. You can put it in full screen mode. Yeah, oh, great. So that's all good.
Thank you. Thank you, Alvaro. And I want to thank you and all the organizers for putting all this together. And thank you very much for letting me also talk about my work. And I'm going to talk about high angular resolution radioastrometry to young stellar objects in the ONC particularly, where we have been working the last few years. So I will repeat something that the core of the ONC is the nearest star forming region where massive stars have recently formed and a distance of 388 parsecs. Many of the young stellar objects are still embedded and non-visible at optical wavelengths, so this is very good to go to radio wavelengths and radio frequencies. The ONC core is rich in compact sources, as we will see, and as also Jaime has already presented. There are many radio sources here in this region, and what interesting thing about the radio observations are that they are usually phase referenced with quasar, and so the astrometry is nearly absolute. So this is a good advantage and why it's good to work at radio frequencies for astrometry. In the past, we have measured the proper motion of a total of 91 radio sources using the BLA observation. And we use archived observation during the last 30 years of the BLA. And we reported these results in 2 different papers. And the first, we report the proper motion for most of the stars, where we study what is the mean proper motions and all the. Also, we did a detailed study on objects that are shown here in this plot in the screen in red arrows, and these 3 are already mentioned many times already. That are the source BN, I, and the source N that have been suggested to be part of the dynamical decay in the past. And so we also found 2 new candidates here that could have been participated also in this dynamical decay of stellar multiple system that are the sources Zapata 11 and IRC 23, and that together with the source X in that presented by Luhmann in 2017. So this could be an example of a multiple system decay. So in our previous work we estimate what was the central position of the sources in the past and when they were the closest approach, and this was in the year 1475, and that and the maximum separation of the sources Bn and I was 120 astronomical units, and we report this. So, but if we want to do astrometry to a highest precision, we can use at radio frequencies. We can use one of the most interesting techniques, that is the very long baseline interferometry, and particularly we can use the instrument that use the very long baseline interferometry is the very long baseline array. The very long baseline array can give resolution below 2 milliards seconds, but one disadvantage is that it only can observe sources with radio sources with high brightness temperatures. So BLBI can only observe non-thermal radio emitters. Fortunately, as has been mentioned also by Jaime, the young stars or young stellar objects can have magnetically active coronas, and that can produce geosynchrotron radio emission. And another advantage of these objects is that they are presented in all star-forming regions, so they are very good target for high-precision radio astrometry. And in fact, we have used these kind of sources to trace the distances to several star-forming regions, and especially the ONC, where we have reported a distance of 388 parsecs. This was led by Marina Kunkel in 2017. And more recent Gaia results have confirmed our results for this and other regions. And so we have used it to several regions. But one thing is that we have few sources per region where we can do astrometry. So it will be very interesting to have a region where we can study many young stellar objects with one single pointing. So a promising case is the ONC itself, where in the past, Jan Forbig reported the compact radio emission from 556 sources, and are shown here in red open circles. So it's a very compact region where there are many sources, and so they can be studied with the BLA, for example, with a single pointing. So they are very important. So if we want to study them with BLBA, so we did new observations to these sources. So this is the summary of our observations. The first one was in October 2015, and 2 more observations were carried in the last 2 years. And also in October, this was chosen because to diminish the contribution of the parallax motion, and we can fully study or only study the motion due to the linear motion of the star. And one advantage of the new abilities of the BLBA is that we can correlate all the 557 fields, and in the past 15-20 years ago it was only possible on one, and we have used this new capability of the BLBA to study now hundreds of sources at the same time. So in one single observation we can observe all these sources thanks to the DiffX software. So the detection criteria was something difficult to constrain, because in almost every single image we contain a flux peaks of above 4 times the signal to noise ratio to the RMS. So we have to to go to a criteria of this. And here we see that restricting the or making flexible the signal to noise cutoff, we can have more and more detections or peaks fluxes in each single image if we diminish the signal to noise cutoff. So, well, what we know is that in VLBI images, there are can be noise peaks of 6 times the noise level of the image. So what we decide to do is to do a selection criteria. So we have grouped our selection criteria. So in the first selection, in the first criteria, we have the sources that were detected in 2 or more epochs. And a second group was when we have one detection, but it was above 7 times the noise level. And another group was when we have only one detection, but with the signal to noise ratio was between 6.5 and 7. And last category was 2 detections between 6 and 6.5. And so, and 400 source fields, we don't have any detection. So of course, our more reliable detections criteria are the first 2. And in the category C, we have like candidate detections, and in category D, possible detections. So we have, if we follow this criteria, we have at least 80 or a little bit more than 80 detections in the ONC of young stellar objects with non-thermal radio emission. And this is the highest number of young stellar objects detected with non-thermal radio emission in a single region, and a single star forming region. So, and this increased the number for a factor of 1 compared to previous results. So here
you have about 1 minute.
Now that we have the criteria detections, we start to measure the proper motion to those that were detected in more than one epoch. So these are, and we wanted to compare it with Gaia results. And here we have the comparison with Gaia, that the Gaia DR2 epoch is 2015.5. And once that we determined the proper motion, we corrected the position to the epoch 2015.8, that it was our first epoch or observed epoch. And so we see that when the sources, the black symbols here are sources that in these 2 epochs have a separation between below 10 milliarcseconds, and the red ones are between 10 to 200 milliarcseconds. So we see that when they are coincident in position, they are also coincident in proper motion. So another interesting result is that we detect also sources where in the single image we detect more than 2 sources, and in particularly this one where we have a binary system here, a very tight binary system. The separation between the 2 components that are these 2 is 20 milliarcseconds. So this is one of the, to my knowledge, at least this is the first tight binary image in the ONC where 2 components appear. And so these are very important because we can determine the dynamical masses of these stars. So we have initiated also another project where we can measure the masses. We will estimate the masses of these young stellar objects. So that is called the Dynamo VLBA. And so it will be interesting to reproduce these 2 other star forming regions where we have many compact radio sources. For example, this is NGC 63224. And I will leave you with a summary of the results. And thank you very much.
Thank you. Yeah, thank you. So here I have a question myself, because you start having now, I mean, relatively large number of sources, can you see global motions in the cluster, like expanding motion? Can you finally give an answer on this old question about expansion or not?
Yeah. So what we did that with the all BLA results in our paper on 2017, where we have the proper motion for 88 sources. And we try to look for expansion, contraction, or even rotation of the cluster, and we don't see anything above, I think, 1 milliarc second per year. So we don't see any order motion.
And no particular difference between the more massive objects and slightly less massive? Or...
Yes, exactly.
Yeah.
No. But we will look for it now that we have even better estimation of the proper motion.
Mm-hmm. It looks like a really amazing data set to dig into this. So it's a perfect place to show the results. So we are happy that you did. Really good. So do you have more questions from the audience here? So if so Sirk, do you want to join? Yeah, you can come here. So we have a question from Sirk here in Leiden. So he's just approaching the microphone.
Yes. Hello. So thank you for your presentation. I was wondering, does the amount of sources that have proper motions that are quite different from Gaia, does that give you any constraints on how worried we should be about catalog mismatches?
I think no. I mean, the sources that are in red here that are they are the most separated, they don't coincide in position. So I think we are seeing two different stellar components. So Gaia is seeing the optical, probably the more massive component, and probably we are seeing a companion that is less massive and more magnetically active. So this means that we are probably seeing two different stellar components. But that's why we correct the positions to the same, to the similar epochs in Gaia and BLBA, and we see that when they are coinciding in position between less than 10 milliarc seconds, the proper motion are also coincident. So I think that Gaia and BLBA results are coincident.
Thank you
are
very
in agreement.
Thank you.
Yeah, so thank you, Sergio. Thank you very much again. Yep. Okay, and so with this, we end the first session of our Orion Uncover online part. We will be back in about 15 minutes, more or less, so 11:45, if I remember correctly, Central European Summer Time. So stay tuned. Thank you very much, and thank you to all the speakers that participated in this first session.